Hey everyone, in this video we'll be looking at the A-star algorithm. Now A-star algorithm is one of the most widely used searching algorithms, and in this video we'll be seeing why that is the case. So up until now, if we look at algorithms chronologically, we see that we've had three major searching algorithms. So we have our branch and bound, our Dijkstra's algorithm, and the greedy best first search. Now, in the case of branch and bound and Dijkstra, we always chose the shortest path no matter what, and neither of these algorithms had any sense of direction. So, a case where both of these algorithms would struggle is in such an example. So, if we had a graph like this, and we had our starting node here denoted by S, and we had our goal node here denoted by G, if we started our branch and bound and Dijkstra at S, we would see that it would start exploring the closest nodes to it. So that would be that, and that. And then it'll similarly move on there, and it'll essentially explore this entire area before even attempting to go here. Now that's a problem for us because it explores way too many states before even heading towards the direction of our goal. So then we saw the need for introducing the idea of direction. So unlike us humans, all of us looking at this problem would know that would intuitively know that we had to move towards the right to get to the goal. But our AI doesn't know this, and that was introduced in the form of heuristics in our greedy best first search. Now, what greedy best first search does is it maintains a heuristic which tells it how close it is to its goal. So there can be multiple heuristic functions such as your Euclidean or Manhattan distance and so on. And essentially, the simplest of them, the Euclidean, would be taking the direct distance formula, which we've studied in our schools, between 2 points, let's say x1, y1, and x2, y2. It would be x2 minus x1 whole square plus y2 minus y1 whole square, and the square root of that. So that would give you an idea of how far each node is from the goal node. So say we're at this node right now, it would tell us how far we are from a goal. Now, greedy best first search always tends to look at to evaluate its path with respect to the goal node. So consider a start node and a goal node here, and we have a bunch of intermediary nodes. And let's say there was a certain path taken to reach these intermediary nodes. Now, greedy best first search will always move with respect to our goal, and that is denoted by the heuristic function which we just discussed by h of n. Now, that is not the case for branch and bound and Dijkstra. So what they do is they always look for the shortest path, and hence it's always with respect to the starting node. Now, neither of these two ideas, the heuristic and the distance from the beginning, were combined, and that is the case in our A star algorithm. So, what A star does is it combines the best of the three of these algorithms. So, if we denoted our heuristic by h of n and our um, distance from the starting by g of n, which we'll call cost path, we combine them to form this equation, which is our f of n is equal to g of n plus h of n. So now we're taking into consideration both our cost path, that is the path that we've taken so far, the length of the path we've taken so far, and the approximate distance from our goal node. So now let's say we are in a maze, we have a maze problem here. What A star will do is, given a dilemma between two paths to take, it will move in the direction of the goal. So you can see the heuristic of this will be lesser than the heuristic of this, and so it will take this path. Now, let's say it continues on this path and moves down here. At any given point, this combination of our cost path and our heuristic could exceed a different path, say somewhere here. So let's say that this path will actually have a lesser f value than this path. Now, what A star will do is it will temporarily ditch this path and it will start considering this one. And similarly, if we reach, let's say, a point here where we see that our f value exceeds this one, the one here, then A star will come back and revive this path. So that's what A star essentially does. So if you look at animations of videos online that show the working of A star, you'll often see that if we had our start and our goal node, it will start expanding slowly in each direction, but you'll always see that it expands more, more faster in one particular direction. So it'll come forward a certain number of steps here, but it'll also start looking around. And ultimately, you'll see that it'll finally stick to this path, and you'll see the reverse path created to show the shortest path. So there are multiple animations of those online that you can see that's very interesting. So what it's doing is exactly what I just explained, is that it looks at certain paths, and even though it's on the right path, it might see a different path, let's say here, that has a lower f value, and it'll start taking that. Now after it sees that this is an inefficient path, it'll come back to this place and revive this path. Okay, so let's look at a demonstration of how A star algorithm actually plays out when we have a graph like this. So we have our starting node and our goal node, and each of the edges have a certain weight to it, and all the numbers in white is the heuristic value of that node with respect to the goal node. So we start at node S, and we first expand its successors. So that would be nodes A and D. Now we know that our A star algorithm's general equation is f is equal to g plus h, where g is your distance with respect to the goal, and h is your distance with respect to, g is with respect to start, and h is with respect to goal. So this would be called our cost path, and that's called our heuristic. So given A, our cost to go from S to A will be 2, and our heuristic is given as 10, which gives us a total value of 12. And similarly for D, we have 4 plus 10, which is 14. Now obviously we want to minimize our total f value, and so we pick 12 from this. Now throughout this, we're going to make note of a table called in consideration. Wow, that is not the right spelling. One second. Consideration, where we will maintain all the possible nodes that we have as a path, but we do not have not visited yet. So from this, we initially got we got A with an A star value of 12, and we got D with an A star value of 14. From this, we picked A, so we'll cross it out, and we continue on. Now from S we go to A, and now A's successors will be B and D. Similarly, if we compute the cost path of B, will be 2 plus 4, and its heuristic is 6. Therefore, we get a value of 12. And D will be 2 plus 5, because we're going from S to A to D, and our heuristic is again 10. So we have a value of 17. Now we update our in consideration table, and we get B with a value of 12, and we get D again with a value of 17. Now the least of these is again 12, so we cross that out, and D will be our next successor. We continue on with B, and from B we can expand C and E. Now C, one second, let me just copy this diagram here for reference. Yeah, okay. So now we have C and E, and if we compute the value for C, we get 2 plus 4 plus 3, which is 9, and we add the heuristic, which is 2, so we get a total of 11. And then we expand E, and we get 2 plus 4 plus 2, plus the heuristic, which is 5. That gives us a total of 13. Now we update our let me bring that down as well. One second. So now we update our in consideration as well, and we add to it, um, once again, yeah, we add to it our, we have C with an A star value of 11, and we have E with an A star value of 13. Now, the least of all of this in our in consideration table would be 11, which is C. So we cross that out, and that's our next node to be visited. Now, C's children is only G, since we can't go back to B, and we compute our um, value of G, which will give us 2 plus 4 plus 3 plus 7, and the heuristic being 0 because it's the goal node, and we get 6, 9, and 16, I believe. 10, yeah, 16. Okay, now we add this 2 into our in consideration, and we get G with value 16. But we see that we actually have a lower value here. So we go back to this, sorry, actually we have E as our least value, which is 13. So we actually backtrack and we check out this path of E, and we see if that will do us any good, better than the current 16 that we have. So if you look at E, we can possibly go to now D as well as G, and if we expand our compute our D value, it will be 2 plus 4 plus 2 plus 2, and the heuristic being 10, which will give us 6, 8, 10, 20. And if we compute our G value, we get 2 plus 4 plus 2 plus 3, and obviously 0 because it's the goal node, and we get 6, 8, 11 as our value. So we throw this in into our consideration table as well. Excuse me, and we get E of, we get D with a value of 20, and we get G with a value of 11. Now we see our minimum is actually 11, and so we cross that out. And now is when we check, every time we take a value from the in consideration table, we check if our least f value, which in this case is G, is actually our goal node, and we see that it is our goal. And so we can actually stop here, and we obtain our uh, path that we've been looking for, which would now be, if we trace back, we'll see we went from, we went from S to A, we went from A to B, we went from B to C, but then we actually backtracked from here, and instead of doing this, we scraped this out, and we actually just went to E directly, and from E we went to G. So our final path was A, S, A, B, E, and then G. And we see that our total cost was 2423, which gives us 6, 8, 11. Yeah, 11. So that's essentially how our A star works. You see that every time we have a minimum value, although it might not be in our path, in the in consideration table, we actually backtrack, check out that path, and then we move on as such. So yeah, that was about it for our A star algorithm. Thank you.